I'm a little overwhelmed at speaking in front of such a learned audience. We've been having a couple of talks this morning on quantum computing. So my talk is actually going to shift the focus towards soft computing, which is more commonly known now as computational intelligence. And the title of my talk is An Integrated Approach to Computational Intelligence. In this particular talk, I'll briefly review computational intelligence systems. We will look at the subsethood neurofuzzy model, which is a model we've been working on for the past couple of years in my laboratory. We'll see how evolutionary learning has been integrated into the neurofuzzy framework. And then we'll take a look at its parallel implementation and a couple of benchmark applications. Because I didn't know the background of the audience, I've got about 5 or 6 slides which will generally introduce the area. The computational intelligence paradigm is essentially a hybrid of 3 technologies: neural networks, which are well known for their learning and generalization ability; fuzzy logic, which is known for its linguistic information and approximate reasoning capabilities; and evolutionary algorithms, which are well known for their global search. An artificial neuron is essentially a computing element which collects numeric information along weighted pathways into what is called the activation. And the activation is then transformed over a nonlinear function to generate the output signal. Collections of such computing elements can be put into a structured network format. So for example, here on the particular slide which I'm showing, you can see that these computing elements are organized into layers. So you have an input layer along which the inputs come. Then these feed forward the information into a central layer, which is called the hidden layer, usually called the hidden layer. And then the information is fed forward again into an output layer, and finally we get the outputs from the network. So essentially, the information that is coming in the form of numeric vector is being transformed multiple times to generate the output. So this kind of a feed-forward neural network is essentially implementing a mapping from an input space to an output space. And networks such as these are well known to be universal function approximators. Neural networks have got a number of salient properties. For example, we know that they are robust and they are fault tolerant. When I say robust, I mean that I can pluck out the connections from the network and it still continues to operate. Or you can have incomplete input data being fed to the system and still it's able to classify or approximate. And the operation degrades gracefully. It's not like a VLSI system which is brittle. They have the ability for associative recall. That is, you can invoke related memories from one concept just the way human beings do. They are universal function approximators. I already mentioned that. They're capable of generalization, which is one of the most powerful aspects of neural networks. And most importantly, they are capable of adaptation, online and offline adaptation. That is, we can incorporate powerful learning mechanisms into the network by means of which they can learn from numeric data, sensor data, or data which is collected and kept in a database offline. On the other hand, the fuzzy principle is a very different principle. It essentially states that everything in the real world is a matter of degree. And all of us will agree about that. Fuzziness stems from lexical imprecision, the elasticity in the meaning of real world concepts. For example, if I say round or red or long or short, or it takes a short while to get from here to the canteen. So the entire idea of using these kind of words, the meaning of each of these words is different to each of us, because each of us has got our own concepts. And there's an elasticity there. And in fact, the fuzzy engineering, the fuzzy systems, they draw their computational power from this elasticity. For those who are not familiar with the fuzzy set, I've just got one slide on it. Consider a fuzzy concept, numbers close to 4. So if I asked you what are the numbers close to 4, here this particular function is modeling the degree of membership of numbers close to 4. So for example, 4 is definitely close to 4, and 8 is not so close to 4. So I've put in a Gaussian function there. This is my concept of numbers close to 4. You can have your own concept of numbers close to 4. Everybody's got their own concepts of numbers close to 4. And in fact, it is this flexibility which lends the fuzzy systems their computational power. As Jim Bezdek, one of the pioneers of fuzzy engineering, once pointed out, it is this flexibility that makes the mathematicians howl, but the engineers smile. Because with this, we can develop very complex fuzzy engineering systems which actually work in practice. Fuzzy rules literally rule the real world. So if I say things like this, traffic density is high, then keep the green light on longer. So a traffic light controller can be designed based on fuzzy rules like this. Or a boiler control system. If temperature is low and boiler pressure is low, then heater power is high. So all the concepts like high, low, longer, each of these can be modeled as a fuzzy set. The fuzzy set is the mapping from a universe of discourse into the interval 0, 1. You can take a bunch of these rules and put them into a fuzzy system. So the rule base is essentially a collection of these fuzzy rules. And then you have the sensor inputs that are coming in, and they are fuzzified. And when we say fuzzified, we really mean that in each of the fuzzy rules, each of these antecedents like low, or if traffic density is high, we essentially find the degree of membership in each of the antecedents corresponding to the fuzzy rules. Then the inference engine essentially determines the extent to which each of the rules fires. And using consequent information that the degree of firing of each of the rules is used to actually generate and defuzzify to get a numeric output. So once again, from an input space, we are mapping to an output space, and there's, again, a high degree of similarity to the feed-forward neural network that I showed you earlier. In fact, it is now well established that fuzzy systems are also universal approximators. So really, the neural network and the fuzzy logic paradigms are complementary technologies. And we can benefit greatly if we are able to integrate these two technologies. So for example, if I take the learning ability and structured representation of the neural networks and combine it with the linguistic rule-based processing ability and the ability to manage uncertainty in the fuzzy system, put them together, we get fuzzy neural systems which can draw on the computational powers of both these technologies. So whenever you're trying to integrate, there are lots of issues that are going to arise. For example, one of the major issues that arises in the design of these systems, and I'll talk about this in the end of the talk also, is the selection of the architecture. Like, what is the number of rule nodes we should use? What are the essential features you should use in a classifier? How do we estimate the weight parameters? Conventional neural networks use gradient descent, but there are lots of other techniques that can be used. For example, we can use evolutionary computation to estimate the weights also, very efficiently. How is knowledge represented in the network? What is the mechanism of inference? What is the learning mechanism? As I already mentioned, we can use evolutionary computation here. And very importantly, once the network has learned, then how do you read back information from the network into a human readable format? Computational complexity of these algorithms is an issue which usually a lot of researchers in the soft computing area skirt, but these are also important issues, especially if you want to implement them in hardware or make them as real-time embedded systems. So there we would have to talk about computational complexity if you want the systems to operate in real time. So past couple of years we've been working on developing fuzzy neural inference systems, and I will describe that during my talk, exactly what we've been doing. Our motivation was to develop an inference system that can take both numeric and linguistic type of inputs simultaneously. Usually the models that are available, they take numeric inputs and map them to numeric outputs, or take linguistic inputs and map them to linguistic outputs, or linguistic inputs and map them to numeric outputs. But we want to take numeric and linguistic together and then generate the output of the system. Such a network will be initialized using a linguistic rule base, using expert information, and then it can be refined using a learning algorithm like an evolutionary computing algorithm or a gradient descent type algorithm. And then you can take the information in the network and extract it back and refine the linguistic rule base. So before I introduce the model, I'd just like to show you how we take a fuzzy rule and embed it in the form of a network. So consider the fuzzy rule. If x1 is medium and x2 is small, then y is large. So here I say if x1 is medium and x2 is small, so the medium and the small antecedents are represented as connections from the input nodes to what's called a rule node. Then y is large, and here you can see a consequent connection, and that's also modeled using a fuzzy set. So it's very different from a conventional neural network. The conventional neural network uses numeric connections, but here the network is now using connections which are actually fuzzy sets. You can take a collection of these rules and put them together and you get a network. And the network we've been actually working on is called the asymmetric subsethood product fuzzy neural inference system, or I'll just call it asynchronous. Asynchronous can take linguistic inputs as well as numeric inputs simultaneously. And this information is fed to rule nodes, And then the information from the rule nodes is then defuzzified at the output to generate the inference. Now, because we have linguistic and numeric inputs coming in, we need to have a method of composition. Composition, I mean that if we take the numeric information in a conventional neural network, we take the numeric input that comes and multiply it into the weight. Now, here we're getting an input which is a linguistic value, here we're getting an input which is numeric. We need to have a mechanism for seamlessly composing this information and feeding it to the network. So towards this end, what we actually do in the model is, we take the input which is numeric and we spread it using a Gaussian function on the left and the right asymmetrically, and that's actually just fuzzifying it into a fuzzy set. Linguistic information is in the form of a fuzzy set already. Now, for each feature, we don't know how much to spread it on the left and the right, and so we leave the left and the right spreads as tunable parameters. Now, once we've got the information in fuzzy format coming in, whether it is numeric or linguistic, and the antecedent connections that I showed you here are also fuzzy sets, we compose this information to determine the extent to which the rule node fires by measuring the overlap. So if the input information is compatible with the antecedents to a rule, then the rule should fire to a higher degree. If the input information which is not matching the antecedents of the rule, it should not fire to a large degree. So we introduced the idea of a mutual subset hood based measure for measuring the overlap. This is just a measure which measures the overlap of two fuzzy sets. If they don't overlap, it's 0. If they overlap, it's 1. And it's really a ratio of these cardinalities, and I won't get into the details of this mathematics. There are many kinds of overlap that can occur. That complicates the underlying mathematics and the proof for universal approximation also, but it's not something you can't get around. Once we compute the overlaps between each of these fuzzy sets, then the information that comes to the rule node is aggregated, and we usually aggregate it using the min operator in the conventional fuzzy systems. Here we use the product operator. Extensive simulations in one of the PhD theses of one of my research scholars has shown that product operator has got a much better discrimination ability than a min operator. When I say discrimination ability, I mean that the rule node is able to differentiate extremely well between inputs that are dissimilar from the antecedents than to rule node information that is similar to the antecedents for a rule node. The output is defuzzified using standard center of area defuzzification. Now, there are many ways in which we can estimate the parameters. For example, gradient descent is commonly used. One of the commonly, in fact, the early versions of SUPHONIS, which was introduced in the thesis of my research scholar, Dr. Paul, was a model which used gradient descent. Later on, we started moving into evolutionary computation as a means of estimating these parameters. And finally, we settled on differential evolution learning. This is a standard evolutionary learning algorithm. The network is represented as a string, and there is a population of these strings, and they cross over, they mutate. Each one has a fitness, and the fitter ones replace the less fit ones, and the population evolves from generation to generation until all the strings converge. So let me discuss a couple of the details of this very briefly. Here is an asynchronous network, and I told you that we have feature spreads here for numeric inputs, and we have a left feature spread and a right feature spread, and antecedent fuzzy sets which are also left, center, and right. So all the numeric values corresponding to each of these fuzzy sets is laid out as a string. But what we did was we introduced an enable bit segment. Now this enable bit segment, what it does is, it's a binary string, and if there's a 1, it shows that there's a presence of the connection. If there's a 0, it shows that this particular connection is absent. So really that marker, it's like a marker bit, which shows the presence or the absence of a connection. Using this implicitly, we can deselect rules or deselect features. If all the connections from the features to a rule node are absent, the rule is removed. If all the connections from from rule nodes to a feature are absent, then the feature is removed. So there's implicitly an ability now in the system to deselect either rule nodes or feature nodes. Now the DE strategy works like this. First, I'll describe it for the real part of the string. You pick a population, a member from the population, let's call it the current member, x1. And you pick two members at random from the population, take their difference, multiply it by a scale factor, and add it to the best member of the population to generate the mutant string. The mutant string then crosses over with the current member to generate the trial string. So that's the real part. And very similarly, we have a binary part. The corresponding binary parts also for the randomly selected members. If the bits are different, we flip the corresponding bit in the best member of the population by 50% probability, with 50% probability. And if the bits are the same, then we do not flip the bits in the best member while we are generating the mutant. Once you've generated the mutant crosses over with the X1 for the binary to binary to generate the trial part for the binary segment trial part for the entire trial vector. We put them back together and evaluate the string for its fitness, and if the string is better, then it replaces the current member of the population. This procedure is repeated for each string in the population, and it completes one generation, and then the generations are repeated. But the essential problem here is that fitness evaluations in any evolutionary computation, as far as the neural networks are concerned, is extremely expensive in terms of time. For example, if you want to run asynchronous learning on McIlglass time series, chaotic time series prediction problem, it takes roughly 14 hours on an X206 3.2 gigahertz Pentium to just complete 5,000 generations. And you need to repeat this process again and again and again. So you can't even attack reasonably large problems if you are trying to use this kind of a learning procedure and you make it serial. So the obvious thing was to make it parallel. So then what we did was we parallelized the algorithm, and we use a standard island model parallelization where we have populations of these strings evolving on different processors, and occasionally there is a migration of strings that takes place over the network. So at regular migration intervals, at random, a processor will select it, a master processor will select one processor, and a string will migrate across the network. So that ensures that you don't have premature convergence in the algorithm. So these exchanges keep going on, and the generations keep evolving, and ultimately we have the populations converge, and we select the best member from all the populations, and that becomes the result. Implementation was done using LAM-MPI. The asynchronous scheme uses both real and integer variables, and so we use MPI derived data types. That helps us save multiple sends across the network if you use the derived data type. I'll describe 3 small benchmark problems on which we tested the model. One of them is the synthetic function approximation problem called the hang problem. It's a very simple system, but I just want to show you how the things work. 50 data points were selected in this interval, and the output was generated. But what we did was we added 2 dummy inputs to this, which are random numbers generated between 1 and 5. And so you got 4 inputs coming in and 1 output, but 2 of them we know have no connection with the output. So our learning procedure should deselect those, and indeed that's what happened. Use a standard squared error measure as the performance. We have 4 inputs to the network, 3 rules and 1 output, and these are some of the parameters. Population size of 530, and we were able to reduce the mean squared error to a very, very low level with successful elimination of the redundant features. So that means the algorithm was working. The asynchronous model was then tested on hepatitis diagnosis problem, which is a standard medical diagnosis problem. The data is available from the UCI repository. The problem essentially is that we have the inputs coming in. There are 16 numeric features and 13 linguistic features, and we want to classify a patient as whether the patient is going to die or is going to live. It's a bit of a murky problem. There are 19 inputs. You can see these are the linguistic inputs that are coming in. These are the 6 different numeric measurements that are available for the patient, and we used a 19 input, 19 Q2 architecture. Q means Q number of rules. And the no and the yes and the male and the female were modeled using these kind of functions, these kind of Gaussian functions. And these were also left as tunable parameters so that the system was able to determine what would be the optimal model for the yes and the no and the male and the female. So we left that also as tunable parameters. 135 patterns in this data set. And we chose 5 sets, each of 70% training, 30% test. And asynchronous was able to do 100% best classification with just 2 rules. So this is something I'll highlight later on. Now it has been established through certain publications also that asynchronous has got a high degree of rule economy. It is able to solve relatively complex problems using a very, very small number of rules. The third example I want to give is the track backer up control problem. It's a standard problem, but I'm not wanting to focus on the fact that we are able to back up the truck. I want to show you something else actually. But I just described this problem. It's a very simple problem. There's a truck and it is to be backed up to the loading dock, and the angle it makes with the horizontal is phi, the steering angle is theta, and so using the value of the x position, the y value is neglected because we assume that the clearance from the loading dock is extremely large. So just using the x value and the angle it makes with the horizontal, we have to predict a steering angle, and then the truck backs up a little bit, and then we predict the steering angle again, and the idea is that you should accurately back up to the loading dock. So that's the asynchronous network up there. X and phi are the inputs, theta is the steering angle, which is the output. Now the data set comprises 238 pairs which are accumulated from 14 sequences. Now there are 14 sequences of backing up. This is published by Wang and Mendel's paper. So the data is available in the Wang-Mendel 1992 publication. And there are 14 sequences where the truck backs up to the loading dock. That gives us 238 pairs of data. You can train the system on 238 pairs of data. There are 14 initial states and they are given here. And the parameters, these are, I'll skip over this. So I'm going to show you the simulations for 3 initial conditions for the asynchronous controller. So here you can see the asynchronous controller is working. It backs up the loading dock, the truck to the loading dock quite accurately. In fact, it has a very high degree of accuracy of backing up the system in just 3 rules. This is a 5-rule system, but then we reduced it to 3 rules, and we also get very accurate backing up trajectories. But there's another aspect I want to highlight, and that is the fact that when you're developing computational intelligence systems, you would like to integrate expert linguistic information seamlessly into the network. So you have expert information and numeric database, and the system is trained partially on numeric data, and then you want to take the expert information and integrate it, and then the system should be able to operate. So what we did was, instead of using all 238 pairs of data, we simply took the first 3 entries in each of the 14 sequences. So we only took 42 data pairs and trained the system on it. So we have a highly reduced data set. Here's a simulation showing the asynchronous controller on extremely reduced data set. Only those 42 data pairs. You can see that it's able to get close to the dock, although not really onto the dock. Then we have 9 rules which are derived from experts as to how the truck has to be backed up. What is the optimal way to back up the truck? And we came up with 9 such rules. So if the position is left and the angle that it makes is left vertical, then the steering angle should be positive big. And each of these positive bigs and positive mediums and centers, lefts and rights, are Gaussian, symmetric Gaussian functions, which I've not shown here. So you can take these expert rules and just plug them into the network and put the whole thing together. So I added 5 rules, expert rules, and you can see the truck is backing up much more accurately. And I added all 9 rules, and I got very accurate backing up there. So the asynchronous network permits us to not only train on partial data, it works well on partial data, but we can easily integrate expert information. And this is a very useful feature of the model. We've tested it in a diverse number of application benchmark problems, some of which I've described, but I didn't describe pattern classification because the time is short. I was given only 30 minutes by Vishal. Function approximation, I described you one problem. Time series prediction, we've tested it extensively on chaotic Mackey-Glass time series, the track backer upper control, and we are now looking at some real world applications also. So the parallel evolutionary asynchronous is an example. I just wanted to give an example in the workshop of an integrated computational intelligence system. This particular model is robust against random data variations. We find it's very economical in terms of the network architecture. It's got a high performance. It's capable of handling the numeric and the linguistic information seamlessly. And it performs in a diverse variety of problem domains. I want to spend a few minutes now on what we are exactly working on these days. What we're actually interested in doing is that we have these networks. For example, the network I showed you in the beginning, but we do not know for a particular application problem, what is the correct number of rules to use, and as to whether the features, each of them is essential for the classification or the prediction problem. This is a very well-known problem, and everybody is trying to find out how to eliminate the features which seem to be redundant or are not important, or try to minimize the total number of rules. So we want to do that simultaneously. So I want to devise a procedure by means of which I can simultaneously optimize both. But I want to do it in two phases now. So in phase 1, I want to do a coarse architecture search, and in phase 2, I want to do a parameter and feature selection. So the idea that came up in a discussion with one, and now one of my research scholars is working on this particular problem these days, Lotika Singh, she's here. She's working on this particular problem. The issue is that now what we're doing is, instead of having a population of networks of strings which represent a single type of rule network, that is only 2 rules or only 3 rules or only 6 rules, and then optimizing it, what we do is we mixed up the population. So we've got population which comprises strings that represent 6 rule networks, 2 rule networks, 9 rule networks. So we've got a hybrid population. And now this population evolves. Each population is evolving on a different processor, on a cluster. But once you have a hybrid population, you need to have a mechanism for crossover, because you want to cross over a string which is say 100 and with 100 entries, real and binary, and want to cross it over with another string which is say 170 entries. You have to have some kind of a crossover operator that not only it makes sense, it should make sense. So what we're actually working on these days is how to on designing that particular crossover operator. We've recently come up with an operator that we are going to be calling VLXDE, variable length crossover differential evolution, in which we use block-based crossover. Block-based crossover means that we have chunks of networks which we pick up and exchange them. So rather than exchanging single connections, we have to exchange chunks. So we pick up a whole chunk that feeds into a rule node and exchange it with another chunk in the other network. So whether it's a 2-rule network or a 9-rule network, it doesn't matter. We just exchange the chunks. So that is the kind of things that we want to do. So we want to optimize it. Now, this particular migration-based differential evolution will now work in the 2 phases that I mentioned. So phase 1 is, what happens is that all the populations, they start converging to a particular rule type. So you start out with all hybrid populations, and then it starts converging to, let's say, 3-rule type. So the populations converge to 3 rules. And there are, of course, a lot of parameters that need to be set. You know, it's not that straightforward as I'm making it out to be, but you have to work with those parameters quite carefully. And but it's working. We're getting pretty good results. So these are some of the relevant publications in which some of this work appeared. This work has been done jointly with my research scholars, and these are the publications. If anybody is interested in knowing more about these models, then I can hand you a copy of these papers. Some of the papers, one of the earliest ones was the substitute product fuzzy neural inference system, the first versions which appeared in 2002, and the new versions, which are the parallel and the migration-based models, have been recently presented last year at the World Congress, and we're still working on this, but we hope to be bringing it to its final completion in a couple of months. So with that, I'd like to end this particular discussion. This is many thanks from the entire Neural Networks Lab team. I'd like to especially mention that this work has been done jointly with my research scholars, Dr. Paul, Dr. Velayatham, who's not here, and Lotika Singh, who's currently working under me. And thank you for a very patient hearing.
Any questions?
A hybrid approach of data fitting. One challenge is that when you go for a neural network for fitting the data, still we don't have an algorithm that takes you to the global minimum. Whereas when you do with the evolutionary computation, that also does locally hill climbing or gradient descent. But because of parallel search, you are more likely to get into the global solution. So have you ever thought about how you can actually combine both these 2 approaches? Because the advantage with the neural network that you have a smooth search, whereas with the evolutionary approach, your search is very discrete. So combining both.
There are actually a couple of models where these hybrid approaches are being used. I've seen them. So evolutionary plus gradient. So they will do one generation and then they do a gradient descent until it stops minimizing, gets to the minimum, the local minimum. Then they will do another generation of evolutionary crossovers, and then they will do gradient descent. But we did not try that yet with our asynchronous model. We have not worked on that. But there are models that are doing that. That's right. They are combining it. And I believe that's also very, very effective.
Okay.
That's an effective approach.